Okay, TSP, phase transitions, and equilibria. Oh my gosh, how many times have we done this one already? So, I'll start off with the most simple example I can give of mixtures, which is a two-state system. In that case, because of how S is defined, we can get that for two identical systems, two identical particles. So let's say that equal numbers of n1 and n2, where these are the number of particles of each species, and total number n is n1 plus n2. And then what we can derive is the mixing entropy, nkb sigma of I ci ln ci is negative nkb c1 ln c1 plus 1 minus c1 ln c1, and c1 is the concentration of the first species. And because we are assuming that
you have total constant concentration.
Yeah, actually let's not assume equal numbers, but we because there's only two species, then the other species has to be 1 minus c1.
So the conversion process is 1 to 1.
Yeah. But this is a constant number of each species. Either that or like for every c1 that converts into c2 is 1 c2 converts back into c1. Yeah.
Yeah, you can't have n c1 converted into 1
Yeah.
c2.
Yeah. So what we do is, so there's this bit in notes about the real expansion to actually calculate the interaction energy, but I'll do a simple treatment here and just say that the internal energy for 1 to 1. So we have to look at like 1 to 2, sorry, 2 to 1, and then 2 to 2. So what we're doing is basically we're thinking about them on a grid and we're seeing like how their interaction energies look.
Did Mel Grosh do this? I don't even remember.
Grosh did this, but
what did I do last year?
This I'm motivating from the Flory-Huggins.
Okay.
I'm not this Grosh didn't do this, but I'm motivating this from Flory-Huggins.
Okay.
Because I'm a soft condensed matter guy. Then what we say is the interaction energy is of this form. U12 plus U22 equals n. So this is interaction energy c squared plus epsilon 2 1 minus c squared plus 2 so 1 2 c 1 minus c. So these are the internal energies caused by the interactions.
Yeah.
U is internal energy from the interactions. So epsilon is the energy caused by
1 next to 1.
1 next to 1. So this is the coordination number.
Yeah.
And put that together, c squared comes out. 1 minus c squared comes out. So this is, this equation is quite intuitive quite easy to understand intuitively.
Yeah.
I actually shouldn't say that, because I hate it when people say that. but this is just 1 1 2 2. This is 2 factor 2 because you get 1 and 2s. And so unmixed. If you want to talk about unmixed, right? This is epsilon 1 1 c plus epsilon 2 2 1 minus c. So this is like we put them into two separate containers. We find the
someone's coughing outside.
it's a water.
Are you sure?
Just water. But yeah,
Are you sure it's the water?
it's kind of watery. It's just quite fun.
The guy who was coughing outside.
Yeah.
The water's sick. I'm so desperate.
Yeah. This is we put it into two containers. We find the individual internal energies, sum it together. Ooh. So, oh my gosh. Okay, yeah. So this tells us that if you find the mixing, which which is the change unmix, and this is 2 and 2 epsilon 1 2 minus epsilon 1 1 plus epsilon 2 2 c 1 minus c, and call this chi, oh sorry, call this kbt multiplied by chi, which is the Fourier exponent.
Yeah.
In soft method.
Mm.
And then this becomes nkbt chi c 1 minus c. So now, briefly we note that for this to be dimension consistent, then chi must have dimensions 1 over temperature.
Also, by the way, the unmixing energy.
Yeah. Or at least should be something like 1 over temperature. Maybe some other factors, but I'm not going to. Yes.
So the interaction energy and the unmixing energies.
Okay.
Oh, I see.
So-
the unmixed energy is always there, right?
Unmixed energy is we're saying that now we've got our two species, put them in two containers.
Mm.
Unmixed energy says that find the individual internal energy of each container, sum those two together, that's the total energy you get from having them unmixed.
Yeah.
Or alternatively, put them in the same container but ignore the interfacial barrier, which is why I don't like that one that much, because we're ignoring the interfacial barrier. Mix is
Yes,
what happens after you.
Yes, the interface, which is what we talk about in the like Pascal's pressure.
Osmotic pressure. Was it?
No, the
No.
surface tension between two species.
Yes. So this is after we mix. So the reason we do this is basically we want to see the Helmholtz free energy and see if the change in this entropy and internal energy from mixing is good enough for it to mix.
Mhm.
So yeah, like the thing is in soft matter we will have to remember something of this form. We have to remember this for the Fourier games. So it's like I'm trying to motivate a intuitive
Mhm.
description.
So mixing energy is defined as the energy difference between.
So yes, the energy difference by causing them to mix.
Yeah.
So if we do this minus TS, mix, C ln C plus 1 minus C ln 1 minus C plus chi C1 minus C. So to motivate this is the entropy term, this is the entropy term, this is a mixing sort of interaction term.
Mm.
Entropy term, mixing energy term. Right.
Yeah.
And then from now on, I don't think I have that many equations. It's all just diagrams.
So now we have the free energy
Yes.
for mixing because we have the mixing energy and we also have the mixing entropy.
Yes. So this whole thing determines whether if it's
Favorable.
favorable to mix or not. Just for this, I'll keep this here later for later. Right. So the diagrams we look at, right, is if we have C, 1 minus C. So far we've actually I forgot to mention that. Well, chi wraps up all the interactions, right? Because of the function. But for now, let's say that epsilon 1 1. So let's say that for simplicity, let's say this is equal to 2. Yeah, but not necessarily equal to epsilon 1 2.
Yeah.
So I can still change.
Symmetry.
Yeah. So what we say is that if we plot f mix over nkbt, we get something that looks like this. So this is for chi equals 3, and then chi equals 2, chi equals 1, chi equals 0. So this is the critical exponent. So because chi is inversely NTB. Huh? What was I writing here? NTBT. So because chi is inversely proportional to the temperature.
So what over NKVT?
The mixing free energy.
Yes.
So chi varies according to 1 over the temperature.
Yeah.
So what we're saying is that when we increase chi, so we decrease the temperature, it goes down, the curve goes down for the mixing entropy, so it gets more and more favorable to
demix. To not mix. To mix.
To mix, yes, to mix. Well, depends really, because chi also depends on the interaction energy. So you sort of expect this term to temperature should encourage chi. Yeah. Actually, yeah. Chi is a balance between the energy and the temperature. But it varies as 1 over the temperature.
Yeah, interesting. So depending on the different these free energy curves,
Yes.
demixing is only favorable in chi equals to 3, right?
Demixing
Into
is-
two states.
Yes. Okay. So say I have my free energy curve. This goes into our next part. Free energy curve. If it's concave, is this concave upwards, right? Concave upwards?
I don't know the name.
Concave upwards.
Okay.
So say we take some point here.
So this is not favorable to demix into two states.
This is not favorable to demix because if you demix, then you get 2 states with these
Higher
two.
energy.
Yeah, and the average has a higher energy.
Yeah.
Whereas if it's concave downwards, then this is favorable to demix.
Yes.
So this one will demix.
Mm-hmm.
So demix. Or mix. Oh, sorry. Demix.
So when we talk about things being demixed, we
Yeah.
mean from initially a single solution of a single concentration is separated into two phases of different concentrations.
Yes. So yes. So in this, it actually depends on the concentration of our solution.
Yeah. So for example, in the left curve,
Within
you only demix in the middle part.
Yes, so here we demix, whereas here we'll just maintain a single state, although it can be shifted into 2 states, I think somehow. But yeah, I think it's possibly metastable at some region there.
Yeah, the stability is due to the second derivative.
Yes.
So that's what my case was talking about.
Yes.
If you have free energy curve.
Yeah.
Free energy curve like this.
Yes.
As long as you are above these 2 points.
Yes.
So somewhere here, doesn't matter. As long as your concentration is in between these 2,
Yes.
is favorable as the energy demix.
Yes.
But this part is dynamically unstable, whereas this one is locally stable.
Locally stable. Yes.
So this one is not that easy to
Yes.
demix because you need to overcome the barrier to move to does this even have to do with barrier? I can't remember. But I do know this one is locally stable because of the curvature.
So
It's locally unstable.
this brings us into the idea of the binodal and spinodal lines.
Yeah.
So we have said that second.
What was the critical type to
critical
define?
type? We'll get into that one now.
Yeah.
Actually. So if we look at this thing, right? For it to be stable.
Yeah.
Then your phase boundary has to be on the line where C equals 0, right?
Yes.
So at this point it's stable, it won't do anything.
Yeah.
So this tells you that chi.
Wait, is that the case?
Wait. So if you shift your concentrations, to hit the partial F to hit that condition.
Oh, so yeah, the energy over concentration is kind of like a force. You have no
Yeah.
force.
So what we say is that C equals half is always a solution because of how we define this. What do I actually define the critical chi-star? What do I actually define chi-star? Sorry, one second.
How is the critical chi-star defined?
Yeah, how is it defined?
What was chi called again?
Chi? The not given a name in the notes. I don't
Okay.
think. But in soft matter, it's the Fourier exponent.
Oh yeah.
It might not have been mentioned how they get chi-star. We're not allowed to just take partial F, partial chi-star, right? Because partial chi, right? Because I mean that makes no sense.
No.
Yeah. Oh well. Oh, yes. If you do partial to F,
And make it 0.
yeah, because chi minus 2 minus fuck. Yeah. Then equals 0. That tells us that negative 2 chi, sorry, 2 chi is equal.
What does that mean?
So this defines the spinodal line. So this is the boundary between it being unstable to the mix to sort of, sorry, favorable to the mix and sort of metastable. Okay, actually, yeah, this is quite messy. So I'll just do all this again. So this thing, partial fx partial 0 tells us when it's stable. Like below, like, so this we call the binodal line. Binodal, right? Yeah, binodal. This we call the spinodal line. Spinodal. So 2 chi is equal to C over C minus 1C. I think.
The quadratic equation needs to solve.
Actually, this is not C plus 1, this is just 1. Yeah. And if you look at C equals half, then chi, or when chi is 2, then flattens out or something. But yeah.
So what's the physical interpretation of the second derivative of the concentration with respect to second derivative of the free energy with respect to concentration being 0?
Okay, yeah, that's the part I have the most trouble with. So the one I want to keep. So this corresponds to partial to F, partial C to being greater than 0. This is opposite, right?
Yeah.
So what we're saying is that if it's more than 0, then it's favorable to have two different states. Sorry, it's not favorable to have two different states of concentration. If it's less stable, so I think what this means is that if you look at it sort of like the grid, So you can have something like right, so these are two different, so this and this, two different states.
Yes.
So if it's more than 0, it's not favorable to do this. It's just going to be like evenly distributed one and back.
I see.
Whereas if it's like this, then you will get something that looks like that. It's more favorable to do that. Like small
I see.
localized clusters.
Because chi is t dependent, right?
Yes, chi is t dependent. Chi is 1 over t dependent. Depends on 1 over t. So what the binodal line tells you, so what this term tells you is, when is it energetically favorable to go from an homogeneous mixture to something that's 3 separates sort of. So if you actually look at it, right, so we can actually look at it in chi space C. This is C.
I see. So the chi has t dependence.
Chi has
So that's
chi has
basically
T
telling
dependence.
you when that's the critical temperature when you start to have phase separation.
Yes, yes, yes. And chi also includes the interaction energies as well. So chi will tell you everything.
Yeah.
Chi contains not most, but chi contains a lot of information.
Yeah, if you just solve the second order derivative being 0,
Yeah.
that's going to tell you the mixing and demixing temperature from which it starts to demix.
Yeah. Well, yeah. So
So spin nodal is when you have demixing, binodal is when you don't have demixing.
spin nodal is okay. So this is binodal. This is spin nodal. Spin nodal. One sec. I'll just erase some stuff again. So that's for the chi space. If we look at it in temperature space, right? Temperature space concentration, then what we have is something that looks like. So this is the binodal. This is the spinodal. Yeah. So what we're saying is that below the binodal line, this is absolutely stable. So this separates when it's going to be absolutely stable.
I thought you had more than one binodal line. Yes.
No, that's just one. Like, how do you get more than? Because binodal is defined when you take partial f, partial c to be 0.
Okay.
And then that tells you a function in terms of chi. So this is saying that if we have some concentration c, when is our temperature? What temperature are we going to have that's going to be stable? That's going to be stable. So within this region, we can have some metastability.
Metastability in what sense?
It won't phase separate
Due to what?
unless you hit it hard enough. So this is sort of like
So it's not in the lowest energy state.
this point, I think.
Yeah, I
So
see.
Yeah, if you hit it hard enough, then you can do
Get
that.
across the boundary, get across the barrier.
And above this is unstable, completely unstable. So the spinodal will separate. So spinodal line separates unstable from metastability because spinodal line tells you when it's 0, right? When the second order derivative is 0. So you have, if you think about it so this is 2D f against c. If you think about f in one dimension and c in this dimension, so if I do this, f.
So part f part c equals to 0 means what again?
So part f part c equals 0. That's the condition for stability, right? So part F part C is equals 0 means that
your free energy doesn't change when you change the concentration.
yes. So that's stability. So that means that that has to be stable phase, I think.
Yeah. Yes.
So yeah,
Like
like
you're talking about this one, yeah.
so what I mean is that if we look at it in like something like this might, I think it might look something like that, but I'm not sure. Like this is never in the notes. I just think this is what it looks like. So what we have is in chi space. This is what we're seeing here. Here, or actually in the wrong plane. So this should be C. Never mind. You get the idea. But yeah. So
Do you mean that should be C or chi?
this should be C, I think. But then that screws up the whole graph. So I'm not going to try to fix it because it's complicated. But the idea is this: if we look at it in 3D space and we take a slice, then we get something that looks like that. Where this term then tells us when we are sort of here, like this tells us when we're sort of in this region. So that's why we have unstable here. So above this is unstable. So it's I hate that polar diagram. But like, yeah. So this corresponds to having these points. This corresponds to sort of having these points, and the rest is below, I think.
Yeah. So the second derivative being 0 also implies the first derivative being 0.
Second derivative being 0 does not imply the first derivative is 0 if I have a curve that looks like that. So x cubed.
Yeah, it doesn't. I'm just saying it doesn't. It should not. So that means. Yeah.
Yeah, but it's saying that for it to be stable, and then for it to be stable and for it to be absolutely stable is a subset of a condition for stability. If it's absolutely stable, then it's definitely stable.
Oh, so anything on the top of these curves. So the two curves for the second order derivative.
Yeah.
In the middle, both of them are stable.
Here, yes, they are both
stable.
Stable. The difference is
this one is absolutely stable.
This is not.
That one is, and the left one will never have phase separation because of the energetics. And the right hand side one,
unless you're in this region.
Yeah, it's metastability. Metastability, you can kick it over the barrier. And the right hand side, it's stable in the middle only.
Yes.
But it's always favorable to demix because of the because it's in the it's above the spinodal line.
Yes.
So it's always unstable because phase separated into two different states.
Yes.
And the left hand side one is basically saying the metastability.
Yeah. Which one? Sorry? This one?
Let me see.
Metastability is not included in these two diagrams, but it is included here.
Which one is metastable in that one?
Here, these 2 points, these 2 areas are metastable, I think. This is included in the notes. Not sure. It might be. I think. I need to check, but I do think it is that area. So the thing is, this spinodal line denotes when it's stable, right? When the phases are stable. So if I have a concentration here, then its phase separates into these two. Right.
Yeah.
Whereas if I put something here, it can't phase separate because it doesn't lie on the spinodal line.
If you're inside the spinodal,
yeah,
it always phase separates into lowest energy binodals.
Yes.
If you are between the spinodal,
within the binodal, it has to phase separate to lie on the binodal.
Yeah.
Whereas if I put it here, it can't phase separate to lie on the binodal.
Whereas if you are between the spinodal and the binodal,
yeah,
it doesn't necessarily separate because that's metastable. Yes. If you're outside the binodal, apparently it does not separate.
Yes.
Yes. And the spinodal is generated by the second order derivative being 0. Whereas the whereas the binodal is generated by first order derivative being 0.
Yes.
Yeah.
I'll skip ahead to the Ising model.
Hmm?
I'll skip ahead to Ising.
Okay.
Because I think mean field theory is more interesting than all this binary phase.
Yeah.
Can I erase this?
Yeah.
Okay, mean field theory. I don't have the notes. I don't have the summarized notes for this, but I will try to summarize my own notes right now.
So you have the lecture notes, you have this set of notes,
These are my summarized notes.
and these are summarized.
Yeah.
Okay.
So yeah. So can I erase stuff? Or
Yeah,
all
erase
this?
them all. Yeah, it's fine.
Okay. Right. So Ising model, I think we've done too much of Ising model by now.
Oh, I've done too much writing on
Too much.
I haven't done that much of analytics. I've done some, I've done a lot of computations.
So Ising model basically, 2D lattice, or 1D lattice, 2D lattice, however you want to say it. The Hamiltonian for the Ising model is something of the form negative mu naught b sigma I n sigma I minus j sigma n sigma I sigma n.
So usually they put like angular, like triangle brackets to say it's near neighbor.
So yeah. So sigma ij sigma I sigma j. So the Ising model is saying that we have a lattice of spins.
Yeah.
The energy is the interaction with the field of each spin.
There's the field and the interaction between your neighbors.
Yes, and this is a sum over nearest neighbor interactions.
Yeah.
J is a sorry. So right, just
And you need to make the mean field approximation for the second term.
yeah, but just a quick note on this. J is not like dipole interaction by magnetic dipoles. It's a sort of spin interaction. So J is not just some dipole because spin, like, it's not just a dipole sort of interaction because that would be too weak.
Mm-hmm.
It's some sort of spin interaction.
It's not purely due to the magnetic.
Yeah, it's
Dipole
not classical, it's quantum.
Yeah.
Yeah, so
It's not like spin orbital coupling we're talking about.
yeah. Just one sec. Yeah, so what we can say is this. I don't actually know where I got this from, but like, so what I'll introduce now is the mean field treatment.
Mm-hmm.
Mean field is so. So mean field is what happens. So if we just look at microstates, it's going to be difficult.
Yes, too many.
Yeah. If we look at microstate, everything gets washed out. We get nothing important, like nothing we want.
Mm-hmm.
So we have to look at somewhere in between. We look at the mean field. So mean field can basically, for example, if I have my lattice, and I have my spins. My mean field can tell me in this area what's the magnetization.
Yes, mean field is basically you group up a bunch of spins and take the average.
Yes, and then we can make this continuous, so we can say what's the magnetization as a function of position.
Yeah, so you create it into a field basically.
Yes, so it's going from, and
that's how they did the renormalization group. Basically, you have a coarsening parameter. So let's say you have radius a.
Yeah.
For each point in space, you draw a circle or sphere of that radius. Everything encompassed, you take the average in the sphere, and denote that to be the magnitude of the field at that point.
So that's also how Landau-Ginzburg theory works, right? So Landau-Ginzburg, we say that we guess a form for the free. So Landau-Ginzburg, for example, what was it? We did in soft matter again, the pneumatics and the what's the first one we did before pneumatics?
So the pneumatic crystal is the one with no head.
Yes. So the other one that had a head was
Polar
ones. Yes. Polar pneumatic LCs.
Polar
Liquid
crystals.
So yeah, the idea was that if we have polar liquid crystals, the head points like in the head introduces some interaction energy, some favorable interaction energy that's sort of like the Ising model. And I just touched my face. The idea is we can say that the free energy is expand this because from the symmetry of the system we know that if it points in the other way, it's got to have the same free energy as it points the first way because like axes are not important.
Yeah, because of the symmetry. If you flip everything like backwards, you get the same energy.
So we can guess a form that is going to depend on
only the even orders.
Only the even orders plus maybe some gradient terms maybe.
Yeah.
I squared. And then
You cannot have terms that change sign due to the flipping.
Yeah, so that's Landau-Ginzburg theory. You based on the symmetry of the system, you guess a free energy form.
And
these are all
is Landau-Ginzburg always fourth order?
It depends on how much you want to work on right? So for certain cases
so anything in which you derive or you guess a free energy depending on the symmetry is called Landau-Ginzburg.
I think so. That's how I saw it done. It's never been explicitly stated.
Okay.
But yeah, the idea is we impose the symmetry to guess a form of the free energy.
Yes.
These are coarse grained fields, like fields. In this case, diamortization.
Yes.
For example. In the polar crystal, what was the field again? Or the orientation?
Oh, yeah, it's
orientation.
No, it's not simply the orientation. Yeah, it was simply the orientation. The complicated case is the pneumatic, because the pneumatic you need you need to define that alignment field.
Yes. And then you get fun stuff like topological defects.
Yeah, you need to define that alignment field, which ranges from 0 to 1. You need to define a certain way.
Yeah. But yes, okay. Back to Ising. After that long round. So mean field theory, you can coarse grain and you can do fluctuations.
Yes.
But for
we
now,
don't do fluctuations.
We don't do
God's sake, we don't do fluctuations.
We do actually, but I'll come into that later.
Oh yeah, we do a little bit. Yeah.
I'll come into that later. For now, let's look at p equals 0 for example. Then the partition function is going to be
e to the
sigma. Just e to the beta j sigma I sum I j sigma I sigma j sum over sigma I e to the beta j sum and I equals 1 sigma I 1. Yeah. So it's just this term cancelled out. Partition function e to the beta energy e to the beta h. Negative.
So this is a one-dimensionalizing you're talking about.
Doesn't necessarily have to be a one-dimensionalizing. Yes, this is a one-dimensionalizing. Yes. Is it necessary? Yes, because in this case we have imposed that to go from here to here. But I don't think in this one is general, I think. But in this one is 1D. So x equals plus or minus 1.
Sorry, maybe I'm not correct actually. So the index is just labeling each side. It doesn't necessarily mean any coordinate axis.
You mean for what?
The index of the sigmas.
The index of the sigmas, yes. So for this one, yes, it labels each side. So this, I think, is general. This is general. But this, in this case, this is 1D.
Why?
Because we have said that this then goes to
Yeah,
this, which
because the way you write your neighbors is basically index plus 1, so
yeah,
you're
so
saying
it has to go to only
it's a 1D.
Yeah, it's 1D chain. And we're saying that because this is either sigma I is either plus or minus 1, then we're taking a sum over all the possible permutations.
Yeah.
Which is this, which is sorry, not all the possible permutations, but
sorry, that's beta j what?
just beta j, because x is plus or minus 1. So it's e to the beta j plus e to the minus beta j, then power of n.
Yes.
Because you have two possible configurations.
Yeah.
So that. And then the next one is quoted.
Quartic.
Quoted.
Quarter.
人家的 result 我们来讲好了。Quoted as in so it's on cycle. So this is like there's no proof, there's no derivation. Oh no, there's
quoted.
Yeah.
Quoted. From one second. Oh, that one.
Cycle. Yeah. So and B and not B. B bit so this B and not B,
But I thought we can derive the same result,
we can
but using mean field.
if you want to do it in 1D, sure. If you want to do it in 2D, I don't think we have done. Oh, I don't think we can do it easily.
Wait. Do we not have that for 2D? I thought we can only do 2D because 1D doesn't have a phase transition. I thought, are you talking about Einstein's result for the phase transition temperature? Or the partition function does?
I'm talking about partition function.
Okay. Because Einstein's result is only in 2D, 1D doesn't
Yeah,
have.
we need it to be 2D to have a phase transition. At least 2D.
Yeah.
So now we go into mean field. So what we say is that instead of single spin, we go into an average spin.
So up to now everything has been exact.
Yes. Now we go into an average spin with some small fluctuations on each side. Or not on each side, but on each field. So the pair interactions become mean sigma plus delta sigma I, mean sigma plus delta sigma j. This is just icing again. Then we neglect the. So I'll just skip a few steps. We neglect delta sigma I, delta sigma j, the second order fluctuations. Assume fluctuations sign independent. Then H becomes negative M naught B sum over I sigma I minus half of Z J sum over I mean of sigma squared equals to mean of sigma I minus mean of sigma. Yep. It's half. I just rewrite this. So Z is the coordination number, and then the half avoids double counting. So this is linear in sigma I, because mean of sigma squared.
Sorry, assume delta sigma I what? Site in.
Actually, this should be sigma plus delta sigma I. So come again?
So this, the expectation of sigma is the mean field.
Assume the fluctuations are site independent.
Yeah.
So like your your fluctuations for each is
So fluctuations is uniform throughout the whole thing.
yes, there's an equal probability for getting one of the fluctuations.
They're summed from the same probability distribution.
Yeah. So this is linear in sigma I. So it's a single particle two-state system. H effective. Z J N sigma squared minus M naught E plus Z J mu sigma sum of I sigma I.
I have 2 times Jn,
Yes.
average sigma squared minus m naught b plus, what is that? M naught b plus,
So plus this is a Z
so z is a what?
coordination number.
Okay.
So each side is surrounded by Z neighbors.
Yeah.
Neighbors. No, all of this is not fun. Honestly, all of this is not fun. So yeah.
No worries.
Idea of mean field is yeah. So now the partition function. I'm just is any of this even necessary? Because
Maybe this is in TSP notes,
yes,
not in TP1 notes.
no,
They do almost the same thing because Claudia was referring to TSP.
yeah, but TP1 I remember. I seem to remember a lot more emphasis on Ginsburg than on this.
I mean, Leonard Ginsburg is not even examined in TP1.
But it is in TSP.
It was in TP1.
Yeah, it is. It was examinable in TP1.
Is it? Leonard Ginsburg?
Is it not? I thought
It's
it
not.
was.
I thought it's not.
Then what the fuck are we doing Leonard Ginsburg for? Like, we've done so much Leonard Ginsburg. I don't know. I much prefer Leonard Ginsburg.
Yeah.
E to the negative beta z j sigma squared. Yeah.
So this is achieved by.
Take this in here. Two possible permutation. Two possible outcomes. Sigma is either plus or minus 1. Stick that in there.
So H effective is from the mean
So
field.
H effective is saying that sorry, one sec. Yeah. So this term goes into here. Actually, no, it doesn't. Doesn't, sorry. So one sec. I need to check this again.
So I need to use I'll be back in a minute.
No, H effective is from mean field. I'll use the total.
Minus part Z part beta gives the energy.
Sorry, come again.
Minus part Z part beta gives you the energy.
Minus part z part beta gives you
The excitation in the mean energy.
minus part z part. Yes, yes, yes.
Is it? Or 1 over Z 1. Yes, it's 1
Yeah.
over Z times minus 1 over Z part beta.
So it's partial log z partial beta.
Yes.
Yes, yes, yes. That gives you the energy. Yes,
Yes.
that gives you energy.
Is that a thing we're trying to calculate? Or
Well,
once we have the partition, we already have the
we
partition.
already have the partition.
What is the next thing we want to calculate? We can essentially calculate anything,
With the partition function, we can get the Humboldt's free energy.
which is the thing I was talking
And
about.
the Humboldt's free energy tells us what the equilibrium energy, the mean dynamic moment. Right. Let's skip that because I think at that point we're done with there's nothing more interesting here.
Hmm. It's already 1 o'clock.
So, we've talked about rundown. Should we just wrap it up here?
Yeah.
I don't think the phase transitions part has much interesting to put on, so I don't think I'll